So now let's see how we can go back and forth between spherical coordinates and Cartesian and even cylindrical if needed. So this picture over here is going to be really useful. And let's start first with spherical to Cartesian. And one of the easiest ones to start with is looking at what z is. And you can see it from the picture here that given the way we can draw this pink triangle and how phi is defined, that z is just going to be rho cosine phi, and that comes right out of just trig relationships. So there we go. And then in order to see x and y, notice that we're going to define x and y. We're going to take the point P and you'll project it down to here, and the x and y coordinates will be the same x and y coordinates as this point Q here. So this length here is x and this length here is y. And so notice that the hypotenuse of this blue triangle, which is the triangle from the theta angle, is precisely what we defined as r when we looked at polar and Cartesian. When we looked at polar and cylindrical. So notice r is going to be rho sine phi, and I'm going to keep making the phi really clear here. And that's also because if you just use the pink triangle up above, that length on the very top length has got to be the same as this hypotenuse of the blue triangle. Well, that's going to be important because we know what x and y are in polar and in cylindrical. They're just r cosine theta and r sine theta. So let's write those. Okay, but now I can replace r in terms of spherical with rho sine phi. And so this is going to be the way you can go from spherical coordinates back to the Cartesian. Now let's go the other way. And the easiest way to do it is actually, let's solve for phi first. So notice if we take this actually, even before we do that, let's find rho first. So we know that rho is just the distance from the origin. Oops. Let's get pens, not highlighters. There we go. Okay, so rho is the distance. So it's just going to be square root of x squared plus y squared plus z squared. And what I'm doing over here is I'm doing Cartesian to spherical. Okay, and then theta is the same in both Cartesian and spherical, so that one's easy. It's the same theta that we've been using in cylindrical and polar. We have tangent of theta is y over x. X not equal to 0, so we can use that to solve for theta. All right, now let's just find phi. So let's use this very bottom equation here on this side, and notice that cosine of phi here is going to be z over rho, but we know that rho is the square root of x squared plus y squared plus z squared. So, and I'm writing them this way, tangent and cosine, because you need to take the inverse of these, but you just need to consider what quadrant you're in when you're trying to take the inverse and thinking of exactly what your phi, as a reminder, can only be between 0 and pi. But theta we allow to go a full 360 rotation. All right, so let's try transforming a region. This is take a moment and put it on pause for example 2 and see first if you can just sketch what this region looks like in 3D, because this is a common region that we might need to integrate over. And then see if you can translate it to spherical coordinates, because that's going to be important if we wanted to rewrite an integral over this region in spherical. Okay, so this is a sphere that's shifted up, and its center is at 1, 0, 0, and it has radius of 1. So let's just draw this shifted sphere sitting here at 1, and that means this is going to be 2. All right, so let's come up with how we could write this in spherical. There's several ways to do it. Usually what I do is just take the equation itself and expand everything out. So if we come down here, I'm going to get x squared plus y squared plus z squared minus 2z plus 1 is 1. And then that's going to give me x squared plus y squared plus z squared minus 2z is 0. And now I can just go right into one option is I literally could go back up here, and in the place of x, I could put rho sine v cosine theta. And in the place of y, I could put rho sine v sine theta in the place of z. But I could also notice a shortcut, because x squared plus y squared plus z squared is rho squared. So if you notice that shortcut, you can jump right to that and say that this is rho squared minus 2, and then I can replace z with rho cosine phi from above. And then we solve this. So I would factor out rho from each, and then I'm getting rho minus 2 cosine phi is 0. So this tells me that either rho is 0 or rho is 2 cosine phi. And I want you to notice if rho is 0, that's just going to put us at the origin. And so I can also get rho being 0. I can get the origin point from this subset of the solution if I were just to let phi be pi over 2. So I don't need to include this separate solution when rho is 0, because it happens here when I let phi be pi over 2. So we're just going to think of this as a way of describing it in spherical. And the analogy, what I want you to remember, is when we did this in polar. In polar, if I wanted to rewrite x squared plus y squared minus 2x is 0, and we had this on some homework, we end up getting this shifted circle, x and y. We end up getting that r squared minus 2r cosine theta is 0. So this is all a side note. And we get that that means that r is going to be 2 cosine theta. And so the analogy is that, or why you can think of these as being shifted, is my angle theta I measure from the positive, like theta is measured here from the positive x-axis, whereas phi is being measured from the positive z. So that's one way that, and that's supposed to look like a phi. That's one way you can kind of connect these two. We've seen something similar before. This is just going to give me a two-dimensional circle. This will give me a three-dimensional sphere, because this one here holds for any theta. And so I could sketch this and then rotate around for any theta, and I'll get the same. I'll get a whole sphere instead of just one circle, right? As you rotate this around for any theta. Okay, so let's do a couple examples now, and let's see specifically when I try to convert triple integrals into spherical, how I change my volume element. Like, what does my Jacobian end up being?